Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. We're looking here at an interesting volume perspective. That is the formula derivation for a hemisphere. You know you can do this very easily if you take a volume formula for a sphere, which happens to be 4 over 3 pi r cube, and you were to divide it by 2 because a hemisphere would be half of a sphere in terms of its volume, and you could get the volume as 2 over 3 pi r cube. This is an easy way of doing it, but you wouldn't really learn much here in terms of an integral setup as to how you can take a hemisphere, and you know a hemisphere looks something like a dome, and how can you go about deriving this volume. Simply put, you can do it very well here by an integral procedure, or you can do this shortcut geometrical procedure. Divide the volume of a regular sphere in half and you get that. But we want to derive this using integral calculus, and that's what we will do in this video. The procedure would generally start with you looking at a unit circle which has the formula x squared plus y squared equals r squared. If you were to take this unit circle and modify it such that you're looking at only at this portion right here, at that curve, and then you were to take this curve and you would rotate it around a y-axis, a dynamic rotation about a y-axis, such that this curve in all of its entirety from this domain of 0 up to whatever this might be, like r comma 0, you rotated it, you'd get a three-dimensional figure, and that would, right here would be a hemisphere, and you can give it a three-dimensional attribute to it. A dynamic movement about a y-axis of this curve would be what you would need to do this derivation. You would look at here everything with regards to a vertical axis, and then you know your integration procedure would be regards to dy, which in this case your equations have to be in the x equals format. You would be looking at intervals over here, upper and lower intervals, which are vertically oriented. And everything would stem again from this equation of a unit circle. X here is equal to r squared minus y squared root. That would be the formula that would feed into the volume formula eventually. Your excellent interval determination would arise from you looking at this figure over here. You have an origin y value of 0, and then you have this y-intercept value here of r, because the radius here is r, as you can see r. So you already have an easily established interval 0 to r. Once you've established this interval from 0 to r, we can even look at this figure right over here. If you were to slice out this shape from right here, from this dome, slice it out, you would have what would be a cross section of a circle, and this circle would have a certain radius r, and the area of this cross section would be pi r squared. In integral calculus procedure, what you take is a limit of sums. You would look at all of these innumerable slices you can develop from the base of this hemisphere up to its apex. You would cumulatively add up all of these circular cross-sectional slices, and that would give you your formula, which is why generally the formula here would be lower limit to upper limit, and you would be looking at cross-sectional slices being cumulatively added from a lower to upper limit with regards to this dy. What exactly is the cross-section of this slice? It's not hard. If you look right here from your line of rotation, which is your y-axis, and you look across to your line, you know exactly this. From any point from 0 up to r, looking towards this line, there's a certain distance, and that distance is always radius, r. And that radius is very well annotated right here by this expression. So you already know what your radius is. The distance from this line of axis to the curve is root r squared minus y squared. If you put everything here in this formula, pi r squared, and you run this through this area, you get the cross-sectional area of each of these slices, which will then get integrated. What is this cross-sectional area? It would be pi r squared, or pi root r squared minus y squared whole square. And you can easily determine that, and it's easy. And your area of each cross-sectional slice would be pi r squared minus y squared. So we have our ay, which is this. We have our intervals, which are 0 to r, and all we have to do now is integrate this to determine this volume of a hemisphere. So everything that we've talked about up till now has brought us to this point, and this is easy integral to handle. Pi can come out as a coefficient. You have r squared minus y squared. With respect to dy, when you integrate this polynomial, you're bringing in the y variable. You have r squared y minus y cubed over 3, upper limit r to 0. You plug in the r's. Plugging in the 0 is meaningless because it's a null value. You have pi r cubed minus r cubed over 3. This is just saying like 1 minus 1 over 3, which is a 2 over 3. And you get 2r cubed over 3 with the pi coming in from the outside, and you get the volume over here as 2 pi r cubed over 3, the volume of a hemisphere, easily derived using an integral calculus setup, versus the shortcut procedure of just taking a volume of a sphere and halving it. You don't want to do just that half procedure. You can, but it defeats the purpose of making this a learning experience. So pretty much it's not too hard. Everything here stemming from the unit circle with a rotation around the y-axis of part of that unit circle to give you what ends up being a hemisphere in a three-dimensional aspect, and then you can do the derivation of this hemisphere using the procedure I've shown. And that's all we wanted to show you in this video. Thank you for watching. Have a nice day.